Simulation of a loaded, unfair five-sided die rolled 60 times is recorded with the following results. We can see them here. Calculate the proportion of prime numbers recorded in the simulation. So the prime numbers are the 2, the 3 and the 5. 1 is not prime. So that is going to be 15 plus 15 plus 5 divided by 60, which is 35 on 60, which is 7/12. Determine the mean and standard deviation for the sample proportion of prime numbers in 60 tosses using the results above. Well, the p hat is just going to be 7/12. The standard deviation is going to be the square root of 7/12 times 5/12, that's 1 take away 7/12, divided by 60, and that comes to 0.0636. It has been decided to create a confidence interval for the proportion of prime numbers using the simulation results on page 8. The level of confidence will be chosen from 90 or 95. Explain which confidence will give the smallest margin of error and state the margin of error. So, the 90% confidence interval is not as wide as 95% CI. So 90% has a smaller margin of error. If you're 90% confident of being between there and there, to be 95% confident you have to go wider. The margin of error is half the width of the interval. Now, once again, we can use that formula for n, which we get from the activity, z squared p, 1 minus p over e squared. And we can substitute some values in. 60 equals 1.6449 times 7/12 times 5/12 over e squared, and solve on the CAS, and we get that e is 0.105. Of course, you could just use the activity at that point. Just make sure you show enough work in when there's 3 marks there. This simulation of 60 rolls of the die is performed another 200 times, with the proportion of prime numbers recorded each time and graphed. Comment briefly on the key features of the graph. Okay, well, it approaches the shape of a normal, and make a point about the n being equal to 60, and we've got 200 simulations. So build up picture. The more simulations, obviously, the better the picture you build up. And the distribution centered on 7/12 or 0.58.